Algebra 1, Lesson 21 and Lesson 22. First, we're going to look at one-step equations by multiplying and dividing. Okay, and first we have a couple things to talk about. So first is inverse operations. Well, if we're talking about operations, then we are talking about things like addition and subtraction, which are inverse of each other, or multiplication and division. Another common one is something like taking the square of something and taking the square root. Okay, things that will undo each other. First, we also have the property of the multiplication property of equality, which says if I take an equation and multiply each of the sides by the same number, then the statement will stay true. So if we have A equaling B and we multiply each side by C, then we would say AC is the same as BC. Well, similarly, we can have the division property of equality, where we say I can divide each side by the same number, and the statement will stay true. The only problem is if we try to divide by 0. That's the only time that it will definitely fail. Okay, so any number other than 0, we can divide each side by and get our answer. So let's practice a little bit. If we have something like 8s equals 72, then there's a couple ways we could do it. First, we could say, well, we have 8 times s. So if we want s alone, we should divide by 8 because those are inverse operations. And since I can divide each side by the same number and still have the statement be true, I can find that s equals 9. The other way to think about this is the fact that we can use the multiplication property of equality to say, if I have 8s equaling 72, well, the only way to get s alone, I could use multiplication. The only way is by using 1 over 8, because then I will have 1 over 8 times 8 over 1 is just 1s. So if I do it to one side, I have to do it to the other, and 72 times 1/8 is 9. So we can do this all the way down, dividing by 9, and getting q equals 3. We could multiply each side by 1/6 and get that x equals 8. We can divide by 4. V equals 7. We could multiply each side by 1/12 and get that m equals 5. And we could divide by 7 and get n equals 9. Okay, these are different methods of going about it, either using the multiplication or division property of equality. The goal, though, is to get your variable by itself. Okay, well, if we have certain word problems, we can show them as equations. Okay, so like $7 per hour for a total of 21, we could show that as 7h equals 21, and so on. Okay, we can set up these multiplication and division problems. Let's look at a couple word problems. A hot air balloon flew at 10 miles per hour. Using the variable h, write and solve a multiplication equation to find how many hours the balloon travels if it covered a distance of 70 miles. Well, we have our original equation that we know, that is distance equals rate times time. We can input what we know. Well, we know the distance is 70 miles. The rate is 10 miles an hour, but unfortunately we don't know the time, and we're putting it as h hours, which we can then say, I'm going to divide by 10 to get that h is 7. So we know that it traveled for 7 hours. Okay? Maybe we're given something like this, like a table, where we say, I don't know the inputs. I don't know the inputs x, but I do know the outputs, and I know the function 60 over x. So what x value would give me 1 as an output? Well, you think, okay, well, the only way to get 1 as an output, 60 over something, that would have to be 60 over 60. So my input must have been 60. Okay, so we're trying to find that number, okay, to figure out, all right, what was my input? One way to look at this is to say, all right, well, if 60 over x has to equal 2, well, I could set up a proportion and say, all right, 2x equals 60. So we divide by 2 and get x that equals 30. we could do that all the way down, either logically or putting it in a proportion, so that we get 60, 30, all right? 60 divided by 20 is 3. 60 divided by 15 is 4. 60 divided by 12 is 5. And lastly, 60 divided by 10 is 6. So even if we don't have inputs, if we're given those outputs, we can work backwards to figure it out. Let's look at a couple more problems. All right. If we start with negative 17 equals negative b, well, unfortunately, we still don't have the variable alone. And what we really have is negative 17 equals negative 1b, negative 1 times b, which means if we're going to undo that, I need to divide by negative 1 or multiply by it, either way. But regardless, I get a positive 17 equaling b. And over here, if we want, we could divide by negative 12, or we could multiply by negative 1 over 12. All right, we would want it to be negative so that our n would be a positive n, and our answer is, well, 108 divided by 12, or 108 times a negative 1/12, that's going to give me a negative 9. Because negative 12 times negative 9 does give me a positive 108. Find the width of a rectangle with an area of 126 square feet and a length of 12. Well, we know that our formula is area equals length times width. So I could say I have 126 equals, well, length is 12 times a width. So we could divide by 12 on each side, and that will give me my width. Okay, and it looks like it would be about 10.5. All right. So multiplying and dividing. Okay, you can try those extra problems if you would like. But let's go on to lesson 22. Analyzing and comparing statistical graphs. Basically what we're saying is we have a lot of different ways to display data. We need to be able to interpret it. And the first data display is a common one, bar graphs. Bar graphs are a graphical way to present information using rectangles whose length represents specific values. So if we look to go and interpret this, we need to look at a couple things. First, we need to look at the axes. And on the x-axis, we see we're looking at shoe size. Y-axis, we're looking at the number of students. So if we are looking at how many students in grade 8 wear size 6 shoes, then we go over to this green bar here, size 6. That means, all right, go all the way up to the top, and that's 7 8th graders. 7 8th graders wear size 6 shoes. Another one. How many students wear size 4 shoes? So we look at this graph, this gray one. We go up to the top and say, well, that's about 4 students. 4 students wear size 6 or size 4 shoes. But what if there are multiple bars for one person or one group? Well, in this case, then we can do some comparisons. So, did people do better or worse with or without preparation? Who had the largest difference, and what was it? Well, we can look at this key, which is really important, and we say, all right, without preparation is the yellow, and then with preparation is green. So we say, all right, for John, well, yellow is smaller than green, so for him, with preparation was better. Carla, same thing, with preparation was better. Peter, there's a little difference, but still with preparation was better. Same with Jetser, and same with Darlene. The second question, who had the largest difference? Well, we see, okay, John went from about a 75 to a 90, so a difference of 15. Carla went from 60 to about 75, also a difference of 15. Peter, it looks like he maybe only grew maybe 2.5. Jetser went up by 10 or so. And Darlene also went up by 15. So we would say there's 3 people that had the greatest difference, and that would be John, Carla, and Darlene, all growing about 15 points. Stem and leaf plots are actually pretty cool and a lot of helpful data. So the stem tells us our tens place, whereas all of our leaves tell us all of the data points and the ones place of all of the data points. So a key that could go along with this would be to say, if I have 2 bar 6, that means that I have the number 26. So each of the leaves, gives me a data point. So if we're looking at the number of cookies that Miss Seneme ate in one day during the summer, then we would say, okay, what number occurs the most? So we're looking over here on our leaves and saying, okay, we have a 2, 6, 7. That's a 22, 26, 27, 31, 33, 35, 42, 44, 46. None of these we have more than one of so far. 57, 58, 59, 61, 63, 64, 65, 67. Well, we actually don't have a mode because all of them occurred just once. What about the median? Well, since all of these pieces of data, I could write out and say, all right, I have a 22, 26, 27, 31, 33, and I could keep going. All of those, 17 pieces of data? Or I can use the stem and leaf plot and realize that it already has it in number line order. We always put our stem and leaf plot in number line order. So I can go and cross off my smallest and then my biggest. Smallest, biggest, smallest, biggest, small, big, small, big, small, big, small, big, small, big. And I'm left with 46. The median would be 46 cookies. And lastly, the range. Well, range is the highest, so we have 67 as our highest, and then our smallest, 22. So our range is 45. So we can see that the stem and leaf plot gives us a lot of data, and technically it's also a visual representation as well, just a little different than what we normally see. In this stem and leaf plot, we have babysitting earnings. So what was the highest fee earned? Well, we're saying I have stems of 2 through 6, so 20, 30, 40, 50, and 60. And so I look at the 60s and I say, all right, one time she got it $61, one time 65. So $65 would be the highest fee. What was the lowest? Well, in those 20s, 21 was the lowest fee earned. How many times did she go babysitting? Well, we count up how many leaves. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 times babysitting. And then lastly, what's the difference between the highest and the lowest fee? Well, that's just the range. So we could say the highest is 65, lowest is 21. So we have a $44 difference. Okay, that's a pretty big range. And lastly, let's just practice doing the median. So I go lowest, highest, lowest, highest, low, high, low, high, low, high, low, high, and I'm to 47. So 47 should be my median. I could use all of this data and also do some other things like mean as well, okay? And of course we could see a median and mode, which in this case we don't have a mode because all of them came up just once. Another way to represent data is a line plot, okay? Line graph. And in this one, we're talking about number of fudge sundaes sold from April to October. So the question is, how many sundaes were sold in May? Well, we go to our months, which is on our x-axis, and we say, all right, May. We go up and we see right there. Well, if we're looking at this going 50, maybe we're going by 5s. 50, 55, 60, 65, 70, 75, we are going by 5s. So on this line, we should have 80. There were 80 sundaes sold in the month of May. Which month were 90 sundaes sold? Well, we see, all right, if that's 80, 85, 90, we're looking at this one right here. And we could say, okay, maybe it crosses there, but that's not in a specific month. That's just the jump between May and June. So we look over here and we say, oh, that's actually a month that I can talk about, and that would be August. So there were 90 sundaes sold in August. You can label each of these parts. All right. So we have a title, we have vertical label, vertical scale. Remember, your scale always is consistent. Horizontal scale and horizontal label. Okay. Going back to this one, this symbol right here comes in handy quite a bit. This symbol, where it kind of breaks the graph, tells us that, yes, we know there are other numbers before 50, but we don't want to list all of them. We're going to start with 50 because that's where my data starts. All right, let's keep going with some of these line graphs. Attendance at 2009 football games. We have football games, numbers 1 through 7, and attendance in hundreds. So estimate the number of people that attended game 3. That means that we're looking at game 3 and we're going right here. Well, it's not perfectly on a line, so we would estimate maybe 375. That seems like a pretty good estimate. How many more people attended game 4 than game 1? Well, we need to know each of those things. Game 1 looks like it had 100 people, whereas game 4 was this big peak and we had 600 people. So the difference would be 500. When do you think the unbeaten season ended? Well, it looks like as they stayed unbeaten, more and more people came. They went up and up and up, but maybe they lost game 4, and so not as many people came to game 5. It looks like their unbeaten season came down on game 4. All right. So choose the most appropriate vertical scale. We have from 50 to 250, 150 to 230, and 0 all the way to 270. Well, if we are looking at this, I would say maybe we have this number of students from 0 to 270, but are we really going to have 0 students? No, we're probably going to have in the higher numbers here, so this wouldn't be a great scale. This one here, number of students, 150 to 230, that might be a better scale if we know that we have more than 150 pieces of data each time. Okay, and same with 50 to 250, although 50 is still a pretty small number of students. So I would say maybe the 150 to 230 is a better amount. And when we see our data, we see, yeah, we only have from number of students 150 to 288 is our highest. So we would want a scale that shows all of that data well. So we would pick this scale over here right in the middle. And that's what we see, 150 to 230. So if we plot these points, year 3 we have a point at 150. Year 2004 we want it at 161, so it's going to be about here. 155, oh, we went down again, so we will be right here for 2005. 2006 is 204. We had a big jump, so we're about here. 210 in 2007. There we are. And 2008, we get 230, so we're going even higher. And 228, our last one for 2009. Let's see if my cursor will drag it over there. Okay, maybe not. Well, imagine that dot at 288. It's not playing very nice with me. It's getting stuck. There we are. Okay, 228. So we can see if we connected these dots, because with line graphs we're going to show that change, we can see a pretty big, steep jump from year 2005 to 2006. The question is, why do you think that jump occurred? Well, if we think about it, there's a lot of different economic reasons. Maybe the housing situation got better and so it drew more people. Maybe a new company opened and so there were a lot more employees that went into that neighborhood. Maybe another school closed down, so they had to move some kids to a new school. There's a ton of different reasons why from 2005 to 2006 there could be a big jump. Okay, a couple more line graphs. We can put 2 lines on a graph. So if we combine these two, we can learn some good things about it. Okay, we can see how the trends changed from grade 6 to grade 7. Okay, and you can answer those questions for yourself. Lastly, our last statistical graph is a circle graph. They compare parts of the circle to the whole circle. The whole circle represents the entire set of data. So if this is the Milton family budget, then we would say, all right, well, if Milton's family spent $4,000 in a month, how much money do they spend for each category? And so we could figure that out. We could do it in many different ways. We could turn all of these percentages into decimals to say, okay, this is 0.21, 0.33, 0.25, 0.06, and 0.15. And then all we would have to do is say, all right, 4,000 times each of those, and we could figure out how much money. So let's do it for one of them. This 0.25, that's pretty easy to see. When we multiply, we would get $1,000 for rent. A quarter of our money is spent on rent. If we do savings, 0.06, we would do 4,000 times 0.06, and we would see, all right, 0, 0, 0, 24, but we have to move it twice, so it looks like they saved $240 each month. And we can continue doing that all the way around so that we can figure out, based on this circle graph, this is how much they spent. Now we can go back and forth. If we know how much we spent, we can then figure out what percentage we have for each part. Well, I hope this was helpful for homework and for studying.